In the University of California Radiation Laboratory's varied and continuing research with experimental nuclear devices and their applications, the availability of a continental test site area to transform ideas into realities permits the most expedient measurement of its progress. Such an area is the Nevada Test Site. Covering more than 600 square miles, it lies between Las Vegas and Death Valley. Roughly 16 by 40 miles, it extends longest north and south. It's surrounded by desert country, a vast, isolated wasteland. A wasteland that is alternately scorched by the summer's heat and blanketed with winter's snows. No fertile farms here. Just arid stretches that seem transfixed in time and clothed in a silence that deafens. Camp Mercury, approximately 65 miles northwest of Las Vegas, is the administrative headquarters of this desert test site, which includes a technical area of approximately 415,000 acres, all under the control of the Atomic Energy Commission. It was first used for an atomic test in January 1951. And since 1953, UCRL has played an important role in the tests that have been conducted at this continental site. Throughout all of the tests, radiological safety has been maintained locally and nationally. 5 miles north of Highway 95, entrance to the main gate of the camp requires clearance or authorized approval on a need-for-access basis. Clearance here is mandatory, but the conditions are not excessively restrictive. Camp Mercury is an atomic city on the boundary of its test grounds, a meeting point for the administrative, scientific, military, civil defense, weather, service, construction, and other personnel who support the test operations. A permanent staff, the UCRL Nevada unit, maintains continuing support at the site and liaison with the laboratory at Livermore. The plain but very acceptable accommodations are ample generally. Following the 1955 test series, when the camp population reached 2,700, additional living quarters were erected. During the 1957 series, the maximum camp population exceeded 3,500. A few miles north of the camp, entrance to the forward or technical area is restricted to personnel with Q clearance. And for access to certain of the compounds within the area, additional security justification is required. Entry to and travel within the forward area, which is completely surrounded by mountains, is subject to AEC security control. Looking down from Control Point, Yucca Basin, a valley roughly 10 by 20 miles, extends northward. It has a good deal of fairly level land and a dry lake on which an air landing strip has been laid out. At the edges of its dry lake, Yucca Basin's graveyards are reminders of the effects of previous tests. The relics have afforded the military and civil defense personnel first-hand data on the effects of nuclear devices. Towers of varying heights up to 500 feet have been the principal means used to hold nuclear devices aloft in the test shots. But before they can be used, there's a lot of earth pushed around. Some very solid steel and reinforced concrete construction, and the laying and covering of a good deal of cable that ties in directly with the tower operation. And while ground crews slug it out below, work proceeds on the towers. Technicians fit the towers with instrumentation for diagnostic study of the various radiations emitted during the time of the nuclear reaction and shortly after. Intense light is produced at various critical stages of the reaction. Pipes under vacuum are directed from specific points down the tower to turning mirrors, which reflect the light to high-speed cameras in a distant underground bunker. And work proceeds at all levels of the towers as the staff from the Livermore Laboratory supervise and assist in the installations of the technical, operational, and appropriate detection apparatus that they have planned and engineered. This is where the payoff to long, hard months of research and development on nuclear devices will take place. There are many types of detectors used to measure the radiation emitted during the nuclear reaction. To maintain a separation of paths to the various detectors so that radiations can be measured unmixed, tons of paraffin are fitted around the collimated lines of sight. Together with lead shielding, the use of paraffin permits a greater number of experiments to be conducted on one device. Film is one of the principal tools used to record the data needed to evaluate the behavior and performance of the program's nuclear experiment. At some distance from the tower is a heavily reinforced underground optical diagnostic bunker. On the surface, its blast door closes automatically, instantly, after the test device is detonated to protect the film and optical equipment within from damage. The cameras inside can measure time to 100 millionth of a second, permitting the capture on film of the fleetest intervals of time. Near the tower's base is a well-sandbagged detector station, designed to shield one of the radiation detectors from extraneous signals. Plywood baffles shield still another light-sensitive detector within a cylindrical housing. Light from the morning star is sufficient to operate the detector. A little further removed is a turret that was reclaimed from a heavy cruiser. It contains several prompt radiation detectors, and its barrel can be elevated and rotated to view a tower scheduled for testing. Another enclosure is the underground electronics bunker, which contains the photoelectric recording equipment. The trailers afford shop and office space during the preparation of the experiments. Within the bunker, ruggedly constructed to provide protection against blast and radiation, the setup and operation of the electronic equipment is a complex and exacting task. Cables routed into the bunker from the detectors transmit current to recording oscilloscopes that are located here. In extensive pre-testing, established signals are picked up on the recording oscilloscopes until they are duplicates of the signals expected during the nuclear reaction. During such dry runs, the diagnostic experiments are rehearsed many times until an accurate rendition of the signal is secured. Finally, preparations are complete to the point that a shot can be scheduled for testing. When the convoy rolls out toward the test site, tension begins to mount at the forward area. For no matter how many nuclear experiments they've shared, familiarity with the process breeds no contempt among the personnel here. While in the program's earlier stages, towers were a maximum of 500 feet high, upon the recommendation of UCRL, this tower has been pushed 700 feet into the sky to effect a substantial reduction of fallout and an increase of radiological safety. Here, the 700-foot tower seems serene, almost as though months of attention to its every whim had beguiled it into a calm acceptance of its own destruction. The convoy rolls forward, and journey's end is ground zero. The final components of the device are transferred to the tower's elevator. It is close to the day for which so many have labored so long. At nearby Indian Springs Air Force Base, jets are made ready for nuclear cloud sampling operations. The jets operate at the nuclear cloud's altitude, making a series of penetrations for a few hours after the event. Samples of radioactive airborne debris for later analysis are collected in the plane's modified wingtip tanks. An airborne UCRL scientific controller directs the various jets to different parts of the cloud, so that the sum total of the samples will represent overall cloud data to provide maximum information on the experiment's performance. Rockets especially designed to collect nuclear debris are a successful new development by the Livermore Laboratory in cooperation with Cooper Development Company. Their use permits earlier cloud sampling than is possible with the jets and penetration at higher altitudes, and eliminates the radiation dosages experienced by the jet pilots. Final checks are made to assure that they are operational, and their flight paths are checked to establish that they are on target. Helicopters are also made ready to move in near ground zero to evaluate physical damage to detector stations in the area and to determine the initial radiation patterns of local fallout. Soon the control point becomes the meeting place for scientific personnel from throughout the forward area. By evening of D-1, all personnel other than those with specific assignments to complete are evacuated from the test area. Before a device is armed, the test director is informed by security personnel that everyone except the arming party is out of the forward area. And before the first timing sequence is sent out, the security guards at roadblock assure the test director that all personnel are evacuated from the forward area. But there's still another check to be made. We haven't learned to control the weather, not yet. Because radiological safety is the prime consideration in the Nevada testing site program, weather reports, particularly regarding wind patterns, will be checked anxiously up to the last minute before detonation. If there's the slightest indication of adverse weather ahead, the test will be postponed. Within the control room, the console operator has completed manual operations in sending the first time signal. The interlocked sequence timer has taken over, and the countdown tape is rolling. However, if there's any reason to halt the test, operations may be canceled manually up to the last second. But apparently every criterion for maximum safety and performance has been satisfied. There is an air of expectancy and an unsuccessfully hidden nervousness among those for whom this is the first nuclear detonation. Older hands take it all in stride. If they're nervous, it's only about their contributions and the success of the experiment. Until now, it's just been theory and work. Soon it will be history. History made in but a few 100 million parts of a second. In one of the helicopters in the air above the zero area, a representative from UCRL directs the survey evaluation. Radiation detection instruments in the helicopters provide spot checks at various locations and altitudes to determine the areas of fallout, checks that are radioed to the control point for evaluation. It is essential to gain access to the area as quickly as possible, as certain of the film data must be recovered relatively soon to minimize film fogging. When the cloud and radiation dissipate, ground monitoring teams will move in by vehicle to plot the fallout contours more specifically. But no entry will be made until the monitoring team's radiological survey is evaluated and the test director approves entry into the area. When the helicopters returned from checking installations near ground zero and retrieving the collector segments of the rockets, the degree of contamination on the helicopters is checked. If they are found to be hot, they are washed immediately and returned to use. When the jets return from nuclear cloud sampling, pilots are removed from the aircraft by forklift so they can avoid contact with the contaminated surfaces of the plane. Careful planning of nuclear cloud sampling flights prevents the danger of pilots receiving radiation dosage that is not within safety limits. Filter papers between their two metal grids are filled with solid debris. They must be handled from a distance, as they are extremely radioactive. The papers are disengaged from the grids in a shielded recovery unit and rolled into cylinders, which are placed in lead-shielded containers called pigs. The pigs, as well as the filters of the collector segments of the rockets, are placed in boxes and shipped by air to Livermore for radiochemical analysis. The experiment is over. The evaluation will begin. The underground testing site, its table-like mountains with flattened tops and sloping sides, lies about 4 miles east and 2,500 feet above the Yucca Basin testing area. Ideally suited to a testing method suggested and developed by UCRL, it was the site used for the first contained underground nuclear detonation. The method affords many testing advantages, such as elimination of air blast, noise, and damage, and the effect of bright flash on the vision of motorists. But more importantly, there is total elimination of fallout and no need to depend upon weather for ideal testing conditions. As instrumentation for underground testing was necessarily limited by the closely confined environment of an underground system, a number of new diagnostic experiments were tried and evaluated as a device of known energy release was used. Various instrumentation was used to measure the yield by shock time of arrival measurements at various points in the medium, as well as the reaction history of the device. The tunnel for the Rainier test was driven horizontally 1,800 feet into the sloping side of the mesa. The zero point was located at 900 feet below the mesa top. The formation in which the shot took place is a porous rock known as Oak Springs Tuff. Similar material deposited from volcanic activity during the Tertiary Age is found throughout the Nevada test site. Within the tunnel, hard hats were a must when moving about. Experiments requiring massive shielding and close collimation are more readily carried out underground than on a tower. When preparations were completed, the convoy made its way up the winding road to deliver components of the nuclear device. Recording stations were ready. The crew prepared to sandbag the tunnel adjacent to the shot chamber. On September 19, 1957, scientific teams that participated in the Rainier test program gathered with responsible UCRL personnel to witness the first contained underground nuclear detonation. Rocks dislodged from the rim of the mesa left trails of dust that formed the cloud that rose about it. But no radioactivity escaped the ground zero region below the surface of the mesa. While UCRL was responsible for the design and execution of the experiment, the technical success of the test is the result of the cooperative efforts of the several scientific agencies. Early in 1957, under the direction of the Sandia Corporation, the operational feasibility of suspending test devices from captive balloons was tried and proven successful. In continuing balloon operations, certain advantages and disadvantages when compared to tower operations are apparent. On the plus side, total fallout is substantially reduced. Cost of the equipment expended in the shot can be 1/10 to 1/20th the cost of a tower, and a balloon test can be scheduled on much shorter notice, since a negligible amount of construction time is needed. However, diagnostic measurements are restricted due to weight limitations and movement, and high surface winds occasionally may cause the delay of a shot, since balloon operations at the Nevada test site were limited to winds of not more than 20 miles per hour. In test operations, the balloon is moved to the shot area, secured with guy lines, and a dummy weight cab is attached. The lights used for detector station and television camera alignment are positioned, and the dummy weight cab is taken to altitude by the console operator. When the cab is in correct position, the television monitors are marked with its location, and collimation of the detector stations is completed. The dummy or load cab is then brought down and detached from the balloon. A few hours before shot time, the shot cab with its nuclear device is attached to the balloon. Television light alignment, anemometer calibration, and control cables are checked. The arming party completes its functions and moves out. And the shot cab is started to altitude when authorized by the test director. All of the facilities that are coordinated with a tower shot, jet and rocket sampling, helicopter survey of the installations near ground zero, and the ground monitor survey of the area, are ready to play their roles. Again, responsible forward area personnel gathers at the control point, and last-minute checks proceed. Countdown goes off manual and on automatic, and moves inevitably toward zero time.
30 seconds until H-1 minute. 10, 5, forward, 3, 2, 1. H-1 minute. Put on goggles or turn away. Do not remove engine or face first until fire advantage is retained. Thirty seconds to zero time. 25 seconds. 20 seconds. 15. 10, 9, 8, 7, 6, 5, forward, 3, 2, 1, 0. The shock wave will arrive shortly. Keep firm footing until wave passes.
The Nevada Test Site program is continuing, providing a wealth of information in the field of nuclear reactions, which scientists translate into new ideas and useful applications. The program is vitally important, but it is only one of the many and diverse research and development programs through which the University of California Radiation Laboratory is contributing to the sum of man's knowledge.